Hello guys, today we are diving into essential concept in computer science, the graph data structure. Graphs are fundamentals in fields like social network analysis, recommendation systems, and computer networks. Let's explore what makes graphs so versatile and powerful. A graph is an nonlinear data structure consisting of vertices and edges. The vertices, also called nodes, represent entities, while the edges or arcs represent connection between the entities. Formally, a graph denoted as G or VE, where V is the set of vertices and the E is set of edges. Imagine a football game. Players are the nodes and the passes are interactions on the field are the edges. This network connection helps us to understand team dynamics and strategies. Just like graphs help us model and analyze relationship in various fields. Let's break down the component of a graph. Vertices or the node. These are the fundamental unit of a graph, representing entities like people in a social network or cities in a map. Edges. These are the connection between vertices. In directed graph, edges have direction while the undirected graph they don't. Degree of a vertex. The degree of a vertex is the number of edges connected to it. In directed graph, we distinguished between in degree, also known as incoming edges, and out degree, also known as outgoing edges. In undirected graphs, the degree simply count all connected edges. Both vertices and edges can be labeled or unlabeled, depending on the type of data being represented. So what are the type of graphs? Graphs comes in many forms, each suited to different kind of problems. Here are some of the graphs that exist. These are some few of these, and so many other graphs are exist in the real world. So, for example, undirected graph, undirected graph, edges don't have direction. Think of a mutual friendship in a social network. Directed graph, edges have direction like Twitter followers. Weighted graph, edges have weight representing things like distance or cost. The Google Maps use this. After that, complete graph. Every vertex is connected to every other vertex. Bipartite graph, vertices are divided into two distinct sets with connection only between sets. Understanding how we move through a graph is a key to many algorithms. Let's explore some important traversal terms. What is a walk? Walk is a sequence of vertices and edges where vertices and edges can be repeat. Think of it as any route you can take in a graph. The trial. A trial where no edge is repeated, but vertices can be revisited. The next one is a path. A path is a trial where neither edges or vertices are repeated. This is the simplest, cleanest route from the vertices to another. Circuit, a trial that starts and ends at the same vertex. Cycle, a path that starts and ends at the same vertex with no other vertex repeated. These concepts help define how data flows to a network, how routes are optimized, and how patterns are identified. Graphs can be represented in different ways depending on the application. First one is adjacency matrix, a 2D matrix where rows and columns represent vertices. The entries indicate whether an edge exists between pairs of vertices and can include weights in weighted graphs. Second one is adjacency list, a list where each vertex has a collection of its adjacent vertices. This is more memory efficient for spare graphs. These representations help implementing graph algorithms efficiently. Let's see some of applications of graph. Graphs have countless real-world applications. Transportation system, social network, World Wide Web, and after that, sport data. Transportation system, Google Maps use graphs to model road, with intersection as vertices and road as edges, calculating the shortest path for navigation. Platforms like Facebook represent users as vertices and friendships as edges. World Wide Web, web pages are vertices and the hyperlinks are directed edges, forming the backbone of search algorithms like Google's PageRank. Resources allocation in operating system. Graphs detect potential deadlocks by identifying cycles in resource allocation. From computer network to biology, graph theory is integral to solving complex problems. In conclusion, the graph data structure is a versatile and powerful tool in computer science and beyond. Understanding its terminology, types, and application open up new ways to model, analyze, and solve problems. Thank you for watching. If you found this video helpful, please like and share and subscribe for more insight into data structures and algorithms. Thank you.